So a very warm welcome from our side as well. Nice that you're here. So in this session, we will be talking about efficient fine-tuning and hosting with LoRa adapters. And we will not only talk about how to fine-tune, but also then how you can efficiently host such LoRa adapters. We, that is myself, Simon Peyer, I'm a solutions architect with AWS, and also
Luca, same solution architect, AWS, we have been represented. Next slide.
Yes, so for today's agenda, we will start with some trends in deep learning. So we will start from there. Then talk about parameter efficient fine-tuning, so how it can be done more efficiently. From that, we will change then, Luca will then talk about multi-adapter inference. So how can you actually have inference on multiple adapters? And then also how you can deploy those adapters, and at the end we will finish off by a demo. So talking about trends in deep learning. So the first trend you observe is that with the multi-model architectures, you have a lot more of possibilities, right? If you think about combining text and images, outputting images, combining video, there are really new applications you can create. The second one is with the models, the bigger ones, the smaller ones, there's people are starting to use such models to adapt them to specific needs. This can be for specific tasks, but it can also be an enterprise, for example, having different customers, and for each customer, they would create their own model, aka a one model per customer pattern. And then the third one is about the model size. We see that there are a lot of smaller new models coming, but also that the bigger models, they keep growing in sizes, and that the new status quo is actually customization. So nearly everyone is not only taking the LLM, but needs some customization. And about this last part, that's where we will be talking about. Just to give a bit of orientation, so there are different common approaches for customization for foundation models. And the first one, obviously, is if you start from scratch, right? You would need a lot of data, you would need a lot of knowledge, a lot of money, and then you can create your own foundation model. It will be very specific to your need, and you really need also a lot of time to do that. If you have a little bit less time, less data, then you can do post-training. So post-training you can do, for example, fine-tuning, where you're taking a base model and just adapting this base model to your needs. What you also can do when you want to have something maybe a little bit faster is to do RAG. So you retrieve data, for example, from a huge corpus of data, and you're augmenting your queries with this additional data. And the fourth approach, which is the fastest one, is prompt engineering. So very fast, you can give some examples in your prompts, and then the output will be adapted to your prompt. So we see there are really different approaches, and when we start from the left side and going to the right side, they are also varying in complexity and also in terms of the quality of what you can get. And in this session, we will be really focusing on the post-training part, more precise on the fine-tuning. The idea there is that you can customize models with your own data, and that you can improve your tasks. So you can really create the model which you need for your specific tasks. But if we do that, we have one challenge. If we want to, for example, fine-tune a 7 billion model, this already requires 70 gigabytes of GPU memory. And this is already an optimized version. So it takes quite a lot of memory to do fine-tuning. And with quite a lot of memory, quite a lot of time, quite a lot of money. So what can we do? Well, something we can do when we would run such a model is to do quantization, meaning you're not running your model at the full weights, but you have your rates a bit lowered in terms of the precision. For example, you have 8-bit or 4-bit quantization. But if you want to do fine-tuning, you would need to do that somehow efficiently, right? And this is called parameter-efficient fine-tuning. We will relate to that to PEFT in the future. And the idea of PEFT is actually that you're not training on all your rates, but you're only training with your data on a subset of the parameters. And this is much faster. It uses much less energy as well. And in the ongoing years and still today, there are many techniques arising around PEFT, and two of them are LoRA and QLoRA, and as said, there are many others. And today, we will deep diving into low rank adaptation. We'll have a look what that is. So imagine you want to fine-tune a model. So we start with a model. A model is separated into different layers. So there are different layers. Here in this example, it's just a simple example with 3 layers. And now, instead of training these layers, we are actually adding adapters. So meaning, for each layer, we would have an adapter. This is one of the key ideas of LoRA. Now, if we zoom in, how would such an adapter look like? So on the left side, we have our layer. This would be from our base model. And on the right side, we have this new construct, the adapter. If we look a bit into the layer on the left side, we see that, as many things in machine learning, it's a matrix. So we are having an input dimension, and the matrix also then produces some output dimension. On the left side, we have a matrix which consists of the in times the output dimension. Output dimension. And now the question is, how can we fine-tune, right? In traditional fine-tuning, you would do the fine-tuning around all this whole matrix, which would take a lot of time. On the right side, the adapter must have the same size, right? Because if it doesn't have the same size, we could not, conceptually, not really working with them at the same time together. And therefore, you would create a matrix in such a way that you can also take the same dimension of your inputs, and it will create also something with the same dimension of the outputs. But you would not like to have the same size of the matrix, right? If not, you would just double the size of your computation. And what LoRA does, that's why it's called low rank adaptation, is actually taking this matrix, and instead of using one big matrix, it's actually using 2 smaller ones. First one, which maps from the input dimension to a rank, which you can choose when you fine-tune R, and then a second matrix, which would, from this rank R, would map again to your output dimension. This is called matrix. This is then created a new matrix. And instead of training on the whole, you would just train those A and B matrices. These both matrices, they have a lot less parameters, and that's why it's actually much more efficient. So again, we see we have matrix A input to R and matrix B R to output. And in the forward pass, when you then would do your computation, you take your data and you can calculate your x prime using the left side, plus you would add the right side. And then when you would update your weights, you would actually not touch the left side, but you would only update the right side. And the idea behind LoRA, one other idea is that actually when you initialize the right side, it's initialized in such a way that it starts with 0. So you would only improve your adapter. Using this concept, instead of having a 7 billion model using 70 gigabytes, you can go down to 16 gigabytes. And if you do one more optimization, if you use on the left side a quantized model, you can even go down to 9 or 5 gigabytes instead of 70. And that's the whole idea to save memory. Now, you will maybe say, okay, that sounds very good, but what's the output? Is it actually good? I will just talk about that in 1 second. Before that, I want to just explain one last thing. If you have the adapter, you can then create many adapters, so you can create 100 adapters. And what you can do is you can then take your original model and you can add your trained adapter, and it will give you then a LoRa fine-tuned model. This works mathematically very well, but this would be the intuition that you can just add the adapter to the original model. Performance-wise, there were many tests done, and I just took here one test, which was done by Anyscale. And we see that we have the different bars, and we see, for example, the darkest one is the baseline, then we have LoRa, and then we have the full fine-tuning. And that we see that for many tasks, actually, the difference, it's not that big between a full fine-tuning and the low-rank adaptation fine-tuning. But in terms of cost, it's really less expensive. Good. With that, I would like to hand over to Luca.
Thank you. So we have discussed about the fact that LoRa is a technique that can be used to create these adapters that can be added or removed seamlessly from models. There is also the option to fuse them into a new model, simply saving the addition of these two, let's say the baseline plus the LoRa. But there are cases, especially in companies that need to serve different customers or need to have, together with the same baseline model, multiple adapters because they want to use the language model for different use cases, and at the same time they want to save costs. There is a problem or an issue. There is the need to address the deployment phase, the inference phase. And this is why I will talk now about how, using a platform that is called Amazon SageMaker AI, it is possible to serve up to hundreds or even thousands of LoRa's using the same base model, using just basically their hardware that is required to host even a single model. Amazon SageMaker is this platform where we can do a lot of things, right? We can build the models, customize them, run inference, FMOps, foundation model operations, formerly called MLOps, and governance. Now, why this platform? Why am I talking about this? Because there are two ingredients that are particularly important when it comes to actually even just the training and then also the inference. If you want to start from scratch, you can go to, I don't know, a GitHub repository and you can find some code and you can run it into your machine. This is not going to be very efficient. Typically, you will need to have containers because it's easier to scale and distribute also across different environments if you need, for instance, just test and prod or something like this. This is why in Amazon SageMaker we have a lot of pre-built containers that contain a lot of libraries with all the correct dependencies that allow you to just take the container and run it. In this case, I'm talking about what we call LMI containers. There is a library for the serving called the Deep Java library that makes a very efficient inference, or makes the inference very efficient. Through this container, for instance, we allow a very fast model download time. If you're talking about gigabytes, this can matter from many minutes to very few. We have a lot of model paralleling frameworks, optimizations, and batching techniques. The most famous are VLLM, for instance, TensorRT. There is also one that is called Neuron X transformers from Hugging Face that allows you to use seamlessly proprietary AWS chips that further can reduce cost. And last but not least, we have this multi-LoRa inference support. We have two libraries. One is called Punica and LoRA that allow you to seamlessly attach and reattach these adapters, as I will show you in a second. So let's start the journey, right? And I will have a demo at the end of it. So another component that is fundamental in how we treat the deployment inside SageMaker is called the inference component. Typically, you have one or more language models that you will need to deploy, but the weights will not occupy the full hardware. Typically, you will have an instance that if you want to save money, you want to have, for instance, 8 GPUs and not 8 times 1 GPU. But how do you make sure that you can occupy efficiently the full hardware? This is the concept of the inference components. So you actually define for each of your models, in this case the base models, how many GPUs need to be allocated for each of these models. What kind of container, what kind of adapters, as we'll see, or model itself will need to be used. And this is then the inference component for the LoRa or for the LoRa adapters, which means that some of the GPU, CPU, or RAM and disk can also be used to seamlessly allocate resources for these adapters that can be loaded and unloaded from the base model. So this allows, if you even just think about the upper part, allows you to load a model that can run inference. You can access the base model plus any of the base plus adapter, so this LoRa fine-tuned, with just the specification of which adapter you need to call. And there's going to be behind, under the hood, really a seamless process of loading and unloading. What about performance? So this is the latency. You can think about the time to first token in terms of number of adapters. You see that the relative, now this is given a model and given architecture, so let's focus just on the relative difference. You can see that the numbers are higher, but still we are talking about very, very efficient. When you go up to 40 adapters, very, very efficient latency serving. And also the throughput, token per second, it decreases a little bit, but it's still very, very efficient, so that you can load a lot of these adapters and still get very, very high throughput, let's say. Now, I have a demo, and I want to show you what we do. Here. So let's assume that we have, everything we do more or less here comes from, in general, we have workshops and whatnot that come from GitHub repository that are public, okay? You can access your AWS account and then this service that is called Amazon SageMaker AI. One of the components, I would say the main component of Amazon SageMaker AI is a Jupyter Notebook server. It's a server on steroids. It has a lot of integrations under the hood, but the interface is what you see. So in this case, what we do, and I have already run it because it can take still few minutes that we don't have in this context, but happy to talk about it later. We are talking about Llama 3 8 billion that we deploy, and the definition of all the environment variables, all the libraries that we want to use is simply through a JSON file. In this case, for instance, we are using LMIDist as an accelerator, and we are specifying some number of maximum LoRa's that can be loaded in a GPU, the ones that can be loaded in the RAM memory, and then all the rest can be loaded into the disk. And we are creating these, we call it endpoint, and then we are deploying them. And after deploying the base model, we create these inference containers, so-called, for the adapters. In this case, what we have been doing, I took some pre-trained adapters that are used to summarize quarterly reports. So this would be, for instance, a report, and the summarization task with and without the LoRA has different semantic similarity to the truth that we expect. And we can do a cross-check, checking that without the adapter, the semantic similarity or the scores, being the Rouge score or BERT score, these are different kind of semantic scores, with the adapter comes closer to the truth. So this is as to say that our LoRA training is effective, and it has increased the proximity of our inference with respect to the expected results. Now, there is an exercise that I want to show you that is quite interesting, which is the following. As I mentioned, we have in Amazon SageMaker with this LMI container the ability to create swaps. So what I mean with that, and I want to show it visually because otherwise it doesn't really, it's not easy to see, is the following. We have 3 layers. We have the disk, we have the CPU, we call it, but it's RAM, and then we have the GPU where the inference is coming. And we have different adapters. So we have capped the size of the GPU adapters to 1, also the RAM to 1, and the disk also can contain 1. So if I swap the adapters from the CPU to the GPU, I will measure a little latency that I want to measure with respect to getting the adapter that is already loaded in the GPU. And at the same time, I want to swap an adapter that is from the disk to the GPU, and then offload the others respectively to the CPU and the disk. And I want to measure the latency, because I want to show you that if we do this exercise, we observe very different latencies. Now, I tried with a little number of tests, that is the table on the top, but we can use the table that is here with a lot of invocations. You can see that if we don't have any swap, so in this case we just have the LoRA that is already in the GPU to make the inference, we have around 1 second for the first time to token. If we instead need to swap the LoRa from the CPU to the GPU and then make the inference, we have on average 10 milliseconds that are added. I mean, 10 milliseconds is really not a lot. And then if a LoRa adapter needs to be swapped from the disk to the GPU, it takes a little bit more, but still 64 milliseconds. So in essence, at the end of the day, we have a way to train LoRa's, which allow us to reduce the cost of the training. And these LoRa's, for instance, take 20 minutes and cost $13 on an 8 billion models. They can be done also on consumer GPU. You don't need the huge machines. So you can start to see the benefit of adopting this kind of techniques. And then at the same time, if you would need to serve multiple LoRa's, there are very, let's say, ready-to-use techniques and technologies like these containers that contain all these libraries that allow you to seamlessly have many different LoRa's that are loaded into your instance, and they can be swapped from disk, CPU, and GPU, depending on your memory requirements and availabilities. And still, you will be extremely fast in serving different queries that come, for instance, from different users, all hosting the model basically on one GPU or the number of GPU, one copy of the model, and seamlessly letting it act as many different models, as many models as LoRa's. I hope that is clear. We'll see from the questions. But I think this is all from our side. Thank you.